Hey Max, what are you working on?
Hi Optima. I'm reviewing some linear optimization basics. I need help, my head is about to turn polyhedral.
Show me what you've got.
Okay, I have no problems with this slide. Just the basic definitions, polyhedron, polytope, nice illustrations, but nothing mind-blowing.
Okay, next.
Now, this slide says that each extreme point of P is defined by the intersection of a set of n linearly independent defining hyperplanes. I remember this from the LP class. For example, in 2D an extreme point is defined by the intersection of two lines in 3D, by three planes and so on.
Sounds about right. Next.
You reminded me of a doctor from that joke.
Which one?
A patient tells the doctor, "Doctor, I have a problem. It seems everyone ignores me." The doctor, to the nurse, "Next patient please."
Ha ha ha. That's tough.
And this is where the tough part starts. The dimension of P in Rn is given by n minus R of P, where R of P is the maximum number of linearly independent defining hyperplanes containing P.
Right. What is not clear?
Everything.
Okay, if there are no defining hyperplanes containing P, then R of P is 0.
Right.
So, the dimension of P is n, meaning that it is full dimensional.
Why?
Look at the figure. What's the dimension of the polytope?
2, I guess.
Why?
Because it has interior points.
Yes, you could define a full-dimensional polytope by saying that it has an interior point, but an interior point is defined using a ball containing that point, and we want to keep things linear.
Okay, I get it. We can also tell the polytope in the figure is two-dimensional by observing that it is not contained in a line.
Exactly. If it was a part of a line, that would reduce its dimension by 1, because our line would be the defining hyperplane that contains it.
Then if it would belong to two intersecting lines, this would give us a point, which is of dimension 0, which is exactly n minus R of P. It is clear now? Every time we add a hyperplane we lose 1 degree of freedom, so to speak.
Great, next slide please.
Oof. A set of points f from P that belongs to the intersection of a non-empty set of defining hyperplanes is called a face of P. That's a weird way to define a face, isn't it?
Makes sense to me. This is a part of the polyhedron that faces the outside, therefore face sounds like a reasonable name for it.
Okay, whether I like it or not I have to face it and accept it. The dimension of a face. Ha. I got a hookup line for MIT students, the dimension of your face intrigues me.
Not funny.
I agree, the definition is not funny at all. But I'm glad it is essentially the same as the definition of the dimension of a polyhedron, and I already figured that out. So, the extreme points are faces of dimension 0, and the edges like x bar x hat are faces of dimension 1.
Very good. Next.
A face f of dimension 1 less than the dimension of P is called a facet of P. So, in our example the facets are going to be of dimension 1, so they are the edges of the polyhedron. I guess the facets are the prettiest faces, right?
Please do not continue with the MIT joke, I got the idea. But the facets are indeed the most important faces of a polyhedron. In fact, they are necessary and sufficient for its complete description in terms of valid inequalities.
So I guess we will be looking for facet-inducing valid inequalities then.
Precisely, we will look for the prettiest faces according to your vocabulary.
That sounds good, but how can we prove that a given valid inequality is facet-inducing?
I believe you have it on the next slide.
Okay, points x1 and so on xk are affinely independent if the k-1 directions xi minus x1 for I from 2 to k are linearly independent. Why in the world do we need another confusing definition of a concept that sounds very similar to linear independence?
Well, this concept is very useful for characterizing facets. Say, if I ask you how you determine that the dimension of a face is n-1, how will you do it?
Good question. But don't we need to show that it is a face first?
Of course we do. I thought you would figure that out.
Sorry, my bad. To show that a valid inequality is a face, we just need to find a point in the intersection of the hyperplane it defines and our polyhedron, right?
Exactly. How about the dimension of the face?
To show it's a facet, don't we just need to show that it belongs to one defining hyperplane?
But what if it belongs to more than one defining hyperplane?
Then the dimension will be less than n-1 and the face is not a facet. So what do we do?
To show that the dimension of a face is n-1, we just need to find n affinely independent points that belong to this face.
Why can't we use linear independence for this?
Okay, let's look at the illustration. Any 2 points in the line segment between x bar and x hat are linearly independent, but how can we use it to say anything about the dimension of the face?
It's an intriguing question.
Not for me. I prefer to focus on approaches that work. Say, if the origin belonged to our polyhedron, the fact that x bar and x hat are linearly independent, that these 3 points, the origin x bar and x hat, are affinely independent. This would imply that our polyhedron has dimension 2, that is, it's full dimensional.
But the origin is not in our polyhedron.
That's right, and the affine independence concept allows us to forget about the origin.
But it's not good to forget your origins. Professor Butenko always talks about Ukraine.
Ha ha ha. Anyway, in the affine independence definition, we essentially pick one of the k points to serve as the origin. In the definition of the slide, x1 is picked, but it could be any other point from the list.
So, any 2 points are affinely independent then?
Correct.
And for 3 points to be affinely independent, they need to form a triangle.
Exactly. #genius.
LOL, very funny. I think I got it. Thanks for elucidating this for me, Optima. This was a huge help.
My pleasure. Now let's get to work.
And what were we doing all this time, may I ask?
Warming up.
That was the heck of a warm-up.